So perhaps we make a start. So welcome to you all to the International Manufacturing Forum series, the March edition on food and digital manufacturing. This is, as perhaps you're all aware, this is an international conference that runs throughout the year, in which each month there is a one-day session on topics selected from the broad range of manufacturing. Now, the Centre for Rapid and Sustainable Product Development, where are hosting the conference. This is a centre of excellence in additive manufacturing, and it's easy for us to think that manufacturing involves engineering, mechanics and such things. But of course, as we've discovered in the COVID crisis, manufacturing of food has been one of the major industries which has been sustained throughout this crisis, whereas other forms of manufacturing have had reduced output. And so it's good to have this focus on food manufacturing, important to us all. So I welcome our keynote speakers from Singapore and from Italy and from Portugal. And when I was looking at the participant register last night, we're getting close towards having 150 registrants for the conference series, and almost half of those people are from outside Portugal. So it's a good international experience. So to start the proceedings, I will ask the president of the Polytechnic of Leiria to make a short welcome speech.
Hi.
Sorry, just a moment, please.
Hi all, it's a great pleasure as president of the Polytechnic of Leiria to be here in this welcome session on the Virtual International Manufacturing Forum Series 2021. Of course, I want to greet all of you, but also I want to greet the chair of the conference, Professor Jeffrey Mitchell, as well all the integrated members of the Center of Rapid and Sustainable Product Development, the CDRSP, including, of course, the director, Professor Nuno Alves. This is a unique event. It's a huge opportunity to discuss the direct and digital manufacturing. In fact, during the whole the year of 2021, we will discuss every month one specific topic that we will share to all of you and with all of the world. In fact, we will go to food and digital manufacturing. In fact, for us, for the Polytechnic of Leiria, but also for sure for the CDRSP, this is a unique and pioneer event, because it's a true open science strategy connected to open and free for all the participants. But I really hope that this outstanding series could be recorded and shared with all the world, not only through the higher education institutions and research units, but also with the companies that are connected with this topic, this outstanding topic of the direct digital manufacturing. Please enjoy all the event during this year of 2021. Thank you for all of you, for all the shares of the conference to participate and to disseminate research with impact to society. Thank you.
Now we can start on today's topic, food and digital manufacturing. Myself and Maria Manuel Gil, who's with us, are the chairs of this conference, and we thank all of those who've agreed to speak. And we particularly pleasure to welcome Professor Antonio De Rosa from the University of Foggia in Italy. And so welcome to you, and we look forward to your presentation from digital image to food product. 3D printing makes feasible the creation of nutritional and sensory personalized food products with unprecedented benefits. Sounds good.
Thank you for your kind invitation for this really interesting international forum on in general additive manufacturing, but this month specifically focused on 3D food printing. So just few seconds to share my screen and to be sure that is possible. Okay. You can see the screen, right?
Yes, right.
Okay. So, again, good morning all. Today my presentation is focused on some specific aspect and ambition of 3D food printing. So the question is, it is possible to use 3D food printing to create personalized food in terms of nutritional point of view, in terms of sensory and also in terms of nutritional and sensory point of view. So for instance, for instance, we can see here a classical figure where we are able to imagine the problem of elderly people. Probably there is a microphone open because I can, yeah, okay, sorry. For instance, for elderly people, there are a lot of problems for mastication and for swallowing. And our question will be also, it is possible to create something with soft material or really able to mitigate this problem. So in general, today, my most important point are three. In general, 3D food printing, main characteristic and ambition potential, where we are in terms of global scenario of our research. And in the last point, I want to share with you some our specific result that we obtained in our lab on this topic. Okay, as you well know, additive manufacturing in general, not for specifically for food, maybe we can resume that AM has three main property, three main ambition: digitalization, the possibility to create some items, some GAT from a CAD model, from digital model. Decentralization of manufacturing, maybe we are able to move to create a transition from the manufacturing in big farm to directly at home, and also customized product. So it is possible to create structure that meet some specific requirement, unique requirement for each people, for each person. But when we skip from additive manufacturing, so I want to remember, yes, sorry, I forgot to include this slide. In terms of additive manufacturing in general, we reached a really unprecedented success. For instance, I want to show you this paper from MIT, Stephen Keating, that with different type of material is able to create very amazing 3D printed structure that are really useful for diagnostic or pre-surgical planning, starting from microtomographic image. So, but what in terms of food? In terms of food, the ambition are more or less the same. The possibility to create new service, new company, new product, the possibility to create tailored food product, and also the possibility to reduce food waste, because one of the most important things is if in the future we will be able to have a 3D printer at home, maybe we can we'll be able also to print just the weight that we want to eat and not more. In general, waste food at home are very important challenges in these few years. And what about customization? When we speak about customization, we have to resume different points: nutritional need, dietary habits, visual aspect, texture, satiety, and other specific needs. In terms of visual aspect, I have included here some new product that Barilla is creating. These are some possibility of 3D printed pasta. You can see the price is very high, about 30 and also 50 euros for pack. But for now, these are used just for specific events. But in terms of visual aspect, we are really close to obtain personalized shape, personalized dimension. So 3D printing, 3D food printing, the main step are really no. We have to plan a desired food. We have to create a digital model. We have to be able to create a printable food formula that is not easy to obtain, because as Professor Hashimoto before me clearly explained, it is very hard to obtain a specific shared thinning behavior. And it is not easy to, for instance, to create a multi-layer material, 10 layer or 15 layer, with avoiding any possibility to create a defect in the structure. Then we have to manage our printing variable. We have a lot of printing variable. Also, in terms of food product, retraction, non-printing movement are really important. It is very different when we want to print food, because rheological material are completely different from ABS or PLA. PLA, thermoplastic material, show a very specific constant property, rheological property for food. When I want to prepare in lab, for instance, dog, printable dog, it is not easy to obtain a rheological property that are fixed every day. So it is not easy to manage printing variable. And then we have to print, and then we have to analyze the printability and the fidelity of printing. But where we are today, in terms of what about the global scientific scenario? I did last 2 weeks ago, research on Scopus database. The first paper, we have approximately 13 years of scientific production. We can see here, this is a really interesting slide, because if in this color we can see the number of paper on printing non-food material, we have more or less 20 kilo of paper, but these in blue color are the number of paper on 3D food printing, and we have 170 documents. So we are in the first step of 3D food printing, and we need many other year of scientific production to reach the quality of additive manufacturing in general. When we create a map, a geographical map, the most important country are China, Australia, although in Italy we have more or less 16 paper, but these are the most important country till now that are focusing on 3D printing. And I want to skip this. This is a map of the co-occurrence of the keywords used in the paper, the author's keyword. We can see the most cited research topic, the most cited research topic. These are the normalized number of research topic. We can see customized food fabrication. We can see platform design, printability, and printing parameter. And also another interesting map is this one. Maybe we can see some islands that are really connected. 3 main islands: personalized food, personalized nutrition, digital gastronomy, platform design, sorry, customized food fabrication. Another big island that include more general terms like rheological properties, printing parameter, innovation, extrusion, printability, dysphagia, that is a really important problem, rheology, and also rheological property. And another small island, the importance of microstructure on food design. We will see later also some result about the effect of 3D printing on microstructure. So here we can see the temporal evolution, the time evolution. The first paper were focused on the printing of chocolate, then the researcher focused their efforts on printing variables, and a lot of paper in a stage 3, in a third step, were focused on the possibility to print a lot of different food material, cereal dough, surimi, fruit and vegetable, a lot of paper recently on hydrocolloids, because hydrocolloids are more easy to print and also are really effective in the resist on the weight of the overlying layers. Rheological property, and probably the most recent application are on programmable food structure and sensory property and 4D printing. We have some example of 4D printing. These are in general some specific example, and probably the most important things is, okay, we have to say that in 3D food printing, the shape are more or less simple shape. We don't have really a complex structure that have be printed in comparison to thermoplastic material. In general, the paper and the researcher printed easy shape and easy structure. What we are able to do and what we need in green, we know very well the effect of gelling agent to increase printability. We have an overall good success in the replica of some simple geometry, like the previous slide that I showed you. And also we know the effect of the basic printing variable, but we have to add a lot of information for this point. For instance, we don't have information on the possibility to print at high resolution, lower than 0.6 millimeter of nozzle. In general, a lot, the majority of paper use, the majority of publication report a nozzle diameter of 1 millimeter, 1.2, 0.8. But what about the possibility to create a very thin filament? We know little in terms of shelf life. It is correct. The previous the previous colleague, sorry, I can't remember the name of the lady, the professor that posed this question. Okay, what's happened after 3D printing? What about the safety? What about the shelf life? It is easy to imagine when we print, you know, a biscuit that we have to cook. We have to reduce water activity lower than 0.4, 0.5. But what about the possibility to print a mix of vegetable and fruit? And we know very little to create nutritional and sensory customized food product. These are also some very popular example that I took from different type of publication. And these are good example of 4D printing, because in the last 2 or 3 years, some researcher, particularly Min Zhang in China and Beshbandar in Australia, they started to think, okay, it is possible to modifying some property along during time, for instance, the shape in this 2 paper, or also the shape activated during microwave heating. Really interesting in this case is to see that after 3, 6, 9, or 24 minutes of microwave heating, we can obtain a different shape. We can improve the shape and change the shape of our structure. Also, 4D printing in terms of color, where the activator is the pH. In this case, the researcher tried to create a multi-layer material. Each layer has different pH, and when 2 layers are in contact, there are some colorant inside that change color during time. And also really important and really interesting is possible to obtain in 4D printing to create flavor development, a change in flavor activated again by a microwave heating. So if I put in microwave heating a different power, maybe we are able to change the flavor that are the volatile compound. Another really interesting point of view that I want to remember, it was obtained from Parinja. Parinja is a professor in Osaka, and also this is application in collaboration with Massachusetts Institute of Technology. Really interesting in terms of personalization, because I want to show you this small video. If we are able, sorry. Okay, what is the main idea? The main idea is, okay, if we are able to change, to program the internal structure, we are able also to create different mastication movement, and this will be able to increase the perception of satiety. So if we are able to plan this, maybe we can help the daily diet. It is really interesting, because from, I want to back again here, from a specific planning of internal structure, maybe we will be able to induce, to create different satiety and satiation perception. Okay, so what about our main progress in this point of view on this specific topics, both in terms of nutritional and sensory property? And what about our main strategy? Our main strategy it is to think about 3D printing as a assembling property and not disassembling properties, because in general, or if we want to use a different words, it is engineering point of view. So we are able to to get programmable, customizable nutritional and sensory property. Maybe what about this? How we are obtain programmable texture, for instance, or programmable nutritional content. I want to show you 3 or 4 examples that we work at this in our lab. So the first one is this paper. Okay, the first idea was, okay, maybe we can plan different cut model, introducing an increased number of pore inside. This is the porosity 18, 22.5, 27, or 2 layers of the same pore with the same dimension. It is possible to predict texture properties. We can see here the fidelity of printing is very good. This is a serial-based dope. In this line of figure, there are the micro tomographic image of this slice. These are the different type of Q14. It is this structure, 4 void or 5 void or 6 void. Q1 is 1 line. So we are showing, I showing here the compression force as a function of distance during a very traditional texture test. And then we used Ashby-Gibson model, really very popular and really important in also different type of field of research. This is the relation between the maximum force at this point, the peak force, as a function of relative density. So if we are able to fit satisfactory the max force, the peak before the biscuit are completely destroyed during the texture test, and if the model fit well, we are able to, to estimate if I want, for instance, a biscuit with a very low F max for elderly people, we have to plan a biscuit with a relative density of 0.35 or 0.3, or also in this extrapolating, it is possible to obtain also some data. So this is a first example, working on the programmable food texture. This is a second example. A second example is based on a different question. We can explore 3D printing to create novel texture property inspired by plant tissue structure. So it is a point of view like biomimicking, very important for different type of field, probably no food research. But what we did is schematically show it here. From original tissue, we acquired the microtomographic image, and from this voxel, then we extracted just one slice, 512 pixels. Then we rescaled from millimeter to centimeter, and this structure was used to create a STL file. And this STL file was used to obtain different model, 2 layer, 4 layer, 6 layer, like with different, crackers with a different thickness. And then we started to print to be able to create something of new. And also the second question is, but we will be able also to predict texture. these are in general, the analysis that we performed, microtomographic image, texture characterization with a 3-point band test. And also we used really popular finite element methods to simulate the stress distribution on the different snack. So we can see the structure, the snack after cooking. This is not raw material, but after cooking. And we can see that more or less the most important pore are respected. Not obviously in shape, because after cooking, some shape is may change a bit, but if we are able in the next slide, sorry, okay, these are two videos just to show you the movement of the printing. Okay, the porosity of the original model was 90, more or less 20. These are the porosity fraction of the raw material before cooking. We obtained a satisfactory capability to replicate the model. And then after cooking in oven, 180 degree, obviously we obtained a really impressive increase in porosity, because during cooking in ordinary oven and during dehydration, what we obtain is the formation, the creation of different new pore and new fracture. But if in terms of visual appearance, we obtained a satisfactory result, what about texture? It is possible to predict this texture. So again, this is the reaction force of the 2-layer, 4-layer, and 6-layer material with a 3-band point texture. We computed also the Young modulus using a very popular equation. And then we started to model our food structure with finite element method. This is the Young modulus as a function of moisture content with a correlation coefficient not really high, but for our aims, we can consider this sufficient. And we used the Young modulus of a reference material with no void inside, absolutely with completely filled crackers. And then we modeled this in with our FEM methods. It is the same application that we can see here. We have two different cylinders, and this cylinder that move before the snack break. Absolutely, we model it in the same way at the same velocity of the experimental test. This is the validated, the experimental black line is experimental value, and the estimated value by COMSOL. And then, okay, the last step was, okay, if we introduce in our model, this is the fully dense 26%, the 40%. 40%, I want to go back just 1 second, because after cooking, we obtained a porosity fraction more or less equal to 40%. So we have, these are the experimental data, and the dotted line is the estimated property. So at 40% of void, we are able to obtain the same result. That means that if we work in this direction, absolutely we need further experiment, but it is possible again to estimate texture properties. And For instance, this is a possibility if I want to start with a different plant tissue image. If I remember well, this is the eggplants, these are apple. Maybe we can create a multi-property material to obtain unprecedented, really new texture traits, texture properties. So again, what about the effect of microstructure? Because when we print, another important question is what's happening in terms of microstructure. To understand and to introduce novel information, I want to skip a couple of slides because I can see that it's 1 p.m. Okay, what we did, we prepared by conventional technology, some snack, these are the 3D printed, and we analyze in terms of microstructure. So we can see that I want to show you, okay, this is the printing experiment. Okay, it is completely different because during the movement, we left some void, some fracture inside. And also inside the filament, we have a porosity distribution that is completely different. I want to show you this, the microtomographic image. You can see the control sample by hand. These are the 3D printed sample. It is very easy to observe the filament and the movement of printing, but this open new fracture, and this has a significant effect on the texture property, the final texture property. I want to show you the differences in microstructure. We have a very big pore here, a very small pore here. So 3D printing effect also has a significant effect on the microstructure and on the number of pore. The 3D printed sample show less pore in number, but big in shape and big in dimension. And also, these are the hardness. This is the hardness. We can see that the hardness of 3D printed sample is higher than the control sample. And last example, last point was to, again, to take one part of this microstructure image and to try to model this by COMSOL, by finite element method. And we can see that experimental stress was about in a very small portion of the 3D printed snack from 2.23, we obtained the estimated stress of 2.45. So we can also use the microstructure image that acquires specifically what's happened inside the filament to obtain a better validation and a better estimation of texture property. That means by all these method, this approach, we will be able to create a structure, soft structure for elderly people or hard structure for young people, for different aim, commercial aim, for hospitalized patients, people. So finally, I want to remember our probably one of the first example, our paper, the possibility to create a nutritional personalizer. We started with the energy and micronutrient requirement for children between 3 and 10 years old. And we planned the printable food formula to satisfy the recommended daily intake, and the recommended daily intake for a snack that in general is reported to be between 5 and 10% of the total RDA. So also we base it on the banana, because for children in general, banana are really appreciated. And we can see here the structure, very simple very simple structure, and this is the cylinder that we obtained. In the previous slides, you can see the effect of print speed, also the flow, that are really important to create a good replica of our 3D printed structure. But in general, we can see that we were able to satisfactorily create our structure. So in conclusion, I want to say that our recent efforts are, in the last 2 years, are put on the possibility to create personalized food by using 3D food printing. Yes, it is possible to create programmable food texture, controlling shape, dimension, and also void generation. It is not easy. We need a further experiment, but it is a really interesting and important hot point for this technology. Also, it is possible to plan the composition of the ingredient used to create a complex food formula to obtain nutritionally personalized food. And then further experiment will allow to alleviate, to mitigate mastication and swallowing problem, or create also novel texture perception in terms of to push on the commercial point of view. Okay, this is the group. I'm part of the group of emerging technology and food formulation here in Italy, and please contact us if you want to collaborate. We will be very happy to collaborate with all of you. Thank you so much.
Great. Thank you very much, Antonio, for a fascinating presentation from which I'm sure we've all learned a lot. So, time for questions and comment, and I wonder if I might start by asking the personalization of food. This sounds a very good objective, and in CDRSP we have similar ambitions. But could you comment on the ability or the current status of collecting digital information from an individual, from a person, so that the food can be personalized? Because a couple of points in your presentation, you fell back onto describing personalized food as for younger people and for older people, which isn't really personalized food. It's just it's adapted. You know, I think you understand the right point. So.
Yeah, absolutely. When we speak about personalization, as you correctly highlighted, we have to speak about the single people, the single person. Yes. Okay, so probably we need also, and this, in my opinion, will be a very interesting possibility of to collaborate with different type of researcher, particularly collaboration with medical, with hospital, because we have to receive unique data, you know, unique requirement of the single person. For now, personalized nutrition and the application of 3D food printing is considered is in a bit wide terms, you know, specific group of consumers, not really personalized for me or for you or for my mom or for my brother. So I believe that in the next 2 or 3 years, when we will be able to create structure for elderly, structure for patients, structure for other type of small group, maybe we will be also able to, for the next step, to create also food for specific people, just for me or just for you. But yeah, you're right. We need to collaborate also with hospital, or with medical center, because will be not easy. Will be not easy.
Thank you. Other questions, comments?
This is also why I asked Professor Hashimoto if with microfluid it is possible to introduce small part of solution, because will be, in my opinion, really useful in terms of personalization.
Yes. Maria, you have a question.
Oh, hello. I need to go
Yes.
my video as well. I'm going to try to. Okay. Well, thank you very much for your presentation, Professor Antonio. I liked it a lot your work, so it's really interesting and fits very well with the kind of activities that we are doing in my lab. So first of all, just to express our interest to collaborate with you in the next future. Secondly, I am interested about what is your point of view regarding the scale up of this technology. Because one of the main bottlenecks of 3D printing for personalized food is to, at least this is our understanding, is how to make this industrial scale in a time framework that could be compatible with mass production.
Yeah, absolutely.
What is your opinion about how to industrialize this technology and to do the scale up? Because for domestic purposes, it's clear that we can spend 1 hour printing something, but for industrial scale, it seems a little bit complicated. No?
Yeah, absolutely. First, thank you for your question, and please send me email, and I will be happy to collaborate with you and to start with another collaboration. Really happy to share our experience with you to create something new. Thank you so much. So, what about mass production? Mass production is really complicated because the most important problem now is fast printing. Because mass production means that we have to to print a lot of pieces in a very limited time. I know I'm collaborating also with some company, for instance, with TNO, that it is really important company. In general, I believe that to use extrusion, it will be a bit hard for now to think in terms of industrialization. And also, I believe that we have to collaborate also with engineering, because we have a lot of problem when, for instance, the rheological property of a simple dough change from today to tomorrow. Viscosity is the most important thing if you want to extrude something. So first, in my opinion, we are our problem, also my problem, that food scientists are moving more or less alone, not with engineering. We have to move, we have to collaborate with engineering to improve the food printer, because food printers in general are a modified printer that comes from PLA. Nothing is produced now specifically for food. That means we don't have software that are able to modulate the printing variable for a dog or for a mixing of fruit and vegetable. if we will be able to collaborate with engineering to create a specific printer for food, for instance, introducing inside some sensor for rheology that is able to measure the rheology of that dog and then to modulate directly and in automatized in directly the movement of the printing, the infill level, and so on, then we will be able to think and to start to think about, okay, maybe we can create 100 pieces in 1 hour. For now, for my knowledge, the only possibility is not extrusion, but it is laser sintering. So to work with powder, because it is fast in comparison to extrusion. Probably there are different type of problem. Probably we have a lot of problem, but for now, it is my point of view. For instance, I don't have experience with laser sintering, but I can see that laser sintering is able to accelerate the process. But my ambition is to work with extrusion, because for laser sintering, what we can use, sugar, powder, or we have to use, but sugar, you can create just a candy. It is completely out, it is completely outside personalized food and healthy food. Or if we will be able to create some powder from vegetables, for instance, also from waste artichokes, for instance, after dehydration, you can create your powder, and then you are able to use this powder during laser sintering. Not easy. In my opinion, and what I want to do is to work with engineering, because it is not inside my skill and I'm not able to modify my printer.
Yeah, fully agree. Actually, this is as well our approach. So the main constraint, the bottleneck right now in additive manufacturing is that the printers are not designed for using with food ingredients, and this is clear that this is one of the main challenges that we have ahead. So for sure, and regarding this particular topic, I have another question. I would like to know your opinion, because one, this is exactly the point. What is the relationship between the physical properties of the food things, so the food ingredients, and the printer variables, so the physical variables of the design of the printer? So do you think that is a good approach, for example, to use I don't know, as you show, banana or potato or mashed potato or something like this? So so how we can achieve the knowledge about the correlation between the physical properties of the soft matter regarding food ingredients and the printability variables of the machine?
Okay. So my opinion is probably the most smart approach is to create to study the relationship with between model system obtained with hydrocolloids and printing variable. When you have acquired a lot of data, we are able to create different hydrocolloids with rheological properties in between the range of, for instance, vegetable and fruits, or dog or chocolate. Then when you have validated this model system, maybe we can start to use ingredients, because I worked with a mix of banana, also other ingredient. Okay, today is these rheological properties, and tomorrow is another one. So it is, yeah. But if you validate, if you are able to validate with hydrocolloids first, and you are able to create a printers that is capable to modulate the variable as a function of rheological property, maybe in the next step of your work will be able also to manage also the natural variability of fruit ripening, something like that.
Okay, so
thank you.
We've had a good discussion. Thank you, Lorenzo. Thank you, Antonio.
Thank you.
Anybody have a quick question? We have, or we move on to the next keynote presentation. And it's a pleasure to introduce my colleague, Maria Moagil from Mare Ipileria, which is based in Peniche on the coast in Portugal. And she's going to talk about marine resources as food material for 3D printing, innovative strategies to improve the efficiency of fish value chain. Please, Maria.
Okay, just let me see if I can. Can I able to share? Sorry.
Yes.
I'm not.
You're already able to share.
Yes, but I'm sorry. Don't know why it's not working. Just give me a second. Can you see the presentation?
Yes.
Oh, okay, perfect. So thank you very much for the introduction and the opportunity to be here to talk more about marine food resources and to open new doors to a new biomass to be used for the 3D printer experts. So just let me talk about a little bit about our research center. We are the Marine and Environmental Research Center. It's a national research center with more than 500 researchers, and we are organized in poles in Portugal, and we are seven poles. We have one pole at University of Coimbra, one pole at University of Évora, another two poles in Lisbon, University of Lisbon, New University of Lisbon, and ISPA, and another pole in Madeira Island, and the last one, the pole of Polytechnic of Leiria, which the headquarters are here in Peniche, near the sea. And we are the only infrastructure dedicated to marine science in the west zone of Portugal. And just let me show you our facilities, which are the headquarters of the pole of Polytechnic of Leiria. Okay, sorry about that, I don't know what happened. And so here in this pole in Polytechnic of Leiria, we are much focused in doing some needed-based research, looking for what the societal needs are and looking for what people need and the industry to help to increase the economic performance of Portugal and the also international level. So we have 3 different main lines, which are blue biotechnology. And here we are doing some bioprospection of marine resources to be applied to develop new foods, food innovation, feed, but also to discover new drugs and to introduce in the cosmetic industry. But also with another research line in marine food resources, much focus in innovation, and also aquaculture and sustainability. Of course, these all 3 main research lines are interconnected, and we are working to help the sustainability of our seas. So here we are mostly focused in working with the industry to add value to the research that we have been working, and this occasion is reflected in more than 100 SMEs partners from the Portuguese partners, industrial Portuguese and also international industries. But today, my presentation will focus on marine resources, trying to help a new door related to this area of additive manufacturing, and trying to see how can marine resources be a potential biomass to the 3D printing industry, and how can we work together to find solutions to have a more sustainable world. As we all know, the population is growing, and we need some more food, but we need healthy foods because we have currently a lot of nutrition issues, and we also need some new foods to prevent hunger, as the global demand for food is expected to double by 2050. So there are lots of issues related to food nutrition, but also to food security. And we know we had seafood as a food resource, which is one of the most important food commodities consumed in Europe, and particular in Portugal. It is very rich in a lot of nutrients like proteins, omega-3s and minerals and vitamins, and is socially, economically and environmentally sustainable, actually more or less. But these type of food are very perishable compared to other products, and only less than 90% of the global fish production is actually used for direct human consumption. The remaining is non-food products or discards or bycatch are not used, and they are very rich in high proteins of high biological value, polysaturated fatty acids, vitamins, minerals, and essential amino acids, which have a positive effect on human health. Also, on the other hand, in September 2015, the Agenda for Sustainable Development was adopted, including 17 development sustainable goals. And it's easy to see that food production involves many of those goals. So we can ask, how can marine resources contribute to reduce the environmental footprint, increase sustainable, and also try to increase the food security, develop new types of food. And so it is vital to start using the aquatic derived biowastes as a possible feedstock for the production of value-added chemicals or materials as a sustainable alternative compared to the exploitation of the more conventional food resources. using a circular economy approach, and obviously trying to reduce the waste is very important nowadays. And so 3 topics must be considered. We need to be much more responsible in our consumptions, trying to find zero waste, not only in food, but also in food. We need to be more sustainable in our food choices, in our food products, trying to use some unexploited products, in this case, unexploited fish, but looking for other marine resources. And of course, we need to guarantee food security. And here we can look for non-traditional foods, try to combine non-traditional foods with emerging technologies, just like additive manufacturing. And so why marine food resources? And why open this new door as a biomass to be used combined with the additive manufacturing? So first of all, our biological resources are limited and we need to feed people. On the other hand, we are very traditional or conservative related to the seafood consumption. So we are fully exploiting a lot of marine species, but there are a lot of them that are not exploited and that are underexploited. And there is a growing need for nutritional and healthy food. And this increases the demand for fishery products from marine reserves, but the productivity is already highly stressed by the excessive fishing pressure, but also with the increase of organic pollution and toxic contamination related, of course, with climate change. So we need to change the way we consume fish. We need to change the way we look to marine resources, but we'll discuss this later. And we need to be non-traditional in our food choices. On the other hand, seaweeds are also marine resources and can be a good source of nutrients. And we know that we have a lot of water in our earth, and there's a lot of marine biodiversity related to seaweeds, but nowadays they are not very consumed, but they are rich in nutrients. We have different types of groups of seaweeds. We are red and green, and they are classified as red, green, and brown seaweeds, depending on what type the species, depending on the nutritional content. And they are now used for energy production, biostimulants, feed, food, cosmetics, nutraceutics, pharmaceutics, and chemicals. And if we look at the economic value of those seaweeds, if you go into the nutraceutics, we can see that the economic value can be high. So it's very interesting for the aquaculture of seaweeds. And we have been looking here in our research group to seaweeds as a marine organism that produce a lot of bioactive compounds, and so it has a lot of interest for to be introduced in the food chain to develop fortified or functional foods. Those bioactive compounds include the antioxidants and antimicrobial activities, but there's a lot of other bioactive compounds that are present in the seaweeds. Depending on the extraction methodologies, on the type of seaweeds, and even on the type of aquaculture production, if they come from the sea or if they are produced in an aquaculture system, we can look and we can find different bioactive compounds. And nowadays there's a lot of emerging technologies that can be used to increase the yield of the extractions, looking for the economic point of view, and different compounds have been obtained with different technologies. We can look at different extraction methods here. We obtain different compounds, and also we obtained different colors. So it's very easy to see that we are extracting different compounds with different colors. And so we know that a lot of seaweeds, they are edible. We still need some regulation here, but they have high commercial value, can have high commercial value. They are easy to produce in a macro scale point, and they have a lot of bioactive compounds, but also polysaccharides and hydrocolloids. So seaweeds can be a biomass, very important, to be linked with traditional foods, to be incorporated in traditional foods, and to develop functional foods or fortified foods to help to promote healthy diets. But also they can be used as a valuable pigment, which is also a problem related here if we looked to the 3D printing technology, mainly with the extraction process. And so we have here an opportunity and the need to develop functional food. There are lots of people that now are looking for some healthy foods, some healthy diets, but also people are going to some limited diets, just like an example, vegetarian diets. And some microalgae are already used as nutritional supplements. Not seaweeds, macroalgae, but microalgae. However, using those micro or macroalgae in the food for the consumption may have certain disadvantages. It has some certain disadvantages, such as of flavors. They are not very easy to consume, depending on the people, but the flavor is different from what we are used to. But they also have an early loss of compounds by functionality. So it's very difficult to produce functional foods with seaweeds and microalgae and introduce into the consumer's diet. So we have an opportunity, and one of the key challenges is to use emergent technologies that help to the introduction of non-traditional foods in the diets, tailoring foods for nutritional needs depending on the physical or medical condition or even life stage. And on the other hand, we have the fish. And we know that there's a lot of fish that is not being consumed. And the fishing, if unidirectional, leads to the absence of natural regeneration of systems, and it's a huge problem for the world. So we need also to have a look at these unexploited fish and byproducts and see how can we use and how can we introduce them in the market, and how can we help to change the way people are used to eat fish. We have been working here looking for unexploited fish sources. People normally resist to new seafood species, so we can try to find some new ways to introduce those species which are nutritional, interesting, rich, and we need to work more based on a perspective of circular economy and try to innovate promoting healthy marine food products using those emerging technologies. These are 5 examples of unexploited Portuguese fish: lira, carapau negrão, minissaia, some of the names in Portuguese, which are not consumed here by Portuguese, and they are very organoleptic, interesting, and also rich in several of nutrients. So they can be also a good source to be used in the emerging technology to be innovated in the food sector. Therefore, research and develop to promote undervalued seafood consumption, reformulation of food products to the consumer nutritional needs, but also encourage more waste use of seafood processing industries while decreasing its environmental footprint is of course very important, and it's of utmost importance to the earth in the world. So we need to innovate to combat food waste and to ensure food security. And so if we have a search for 3D printed food in the internet, we'll find a lot of information. In recent years, numerous studies have been doing and have demonstrated the value of this technology. However, there are a lot of new these studies generate a lot of new challenges, as food materials consist of many different components with different properties, and they should be studied, and we should increase the number of food materials that can be used using this technology. 3D food printing have been mostly used to produce sweet foods and not healthy foods, but we need to have a look into these three technology, as Antonio already said, to increase the nutritional and the sensorial properties of these products. Hence, as already highlighted by Antonio, we are starting the research in this topic. This technology is an innovative, and some say that this is disruptive technology, which is in constant expansion, and seen by the rising number of reviews, book chapters, and research articles are getting attention from the researchers all over the world. So we have here a figure that illustrates the number of publications returned from research containing the keywords additive manufacturing or 3D printing or three-dimensional printing, but also food between 2015 and 2020 in our databases. So we can see that it's increasing a lot, but much more research is needed, and we should be still working and increase the research in this field. So this technology has attracted a lot of attention for its immense potential to tailor food products for specific necessities, but also for specific preferences. It can be, as already mentioned by the previous keynotes, it can be categorized in different categories. Normally, the most commonly used is the extrusion or fused deposit modeling, but we can also find it using inkjet printing or binder jetting, or also selective steering, and bioprinting has also been used in the food sector. Of course, the materials used, if they are present in liquid, powder, or semi-solids, influences the choices of the printing technology, and the extrusions needs required the materials to present high viscosity, whereas inkjet requires low viscosity. Related to binder jetting and selective steering, they both use powdered materials, but the challenge here is how to get how to join the different powders, so we can get more nutritional value combining powders from different food sources. And this is a schematic view how we prepare how we deal with the food printing process. So it involves several steps between the choice of material and the printing and the desired structure. First, we have the selection of the printable material, and we need to study and develop the food formulations, taking into account, of course, the printing process. But here the challenge is how to produce different printable materials, different formulations to increase the nutritional value of those formulations. Second, the model of the desired structure is created using the CAD software, or an existing object is scanned to be used as a model. Third, the model is converted into a STL file and sent to the slicing software, where the model's layers will be created and the printing parameter set it. And finally, we have a G-code file with the dimensional and printing instructions, and sent to the printer. We'll build the desired structure. But then we need to have a look, and we have to study the post-processing, because the post-processing will also influence the nutritional value and the shelf life of the product. So we need to have a look at all the process in a global perspective. Among the referred advantages, of course, there is a lot of limitations and challenges. These type of products are not popular among consumers. Consumers don't have an idea, and it's not very easy to introduce this type of products. Even if this is a potential technology to use the co-products or byproducts of the food processing industry, which is very important nowadays. So those products, being a promising source of valuable substances that possess nutritional properties, are visually unpleasant for consumption, but can be used as printable formulations following the principles of a circular economy and designing out waste and contributing to the sustainable of the ocean and even of the land. So, to date, the use of 3D printing for food has been mostly used to the production of aesthetic shapes for chocolate or pasta products. But the potential should be seen in a different way, in which food can be tailored to the individual needs, incorporating required nutrients while retaining the requirements to be visually pleasing. In addition, it will be possible to guarantee all the organoleptic characteristics to which the consumer in general is familiar, such as the smell, sound, and also the texture. But there's a lot of challenge presently. Despite the many recent advances in 3D food printing, there's still a lot of work to do to find some more printable ingredients. The process is very slow for mass production, and Lorenzo already asked about this, and Antonio already discussed this. This is a question and a point. And of course, we need to work about the consumer's perception. Also, incorporating cooking technologies should be an advantage and will be a good point to increase the mass production, but also to increase the shelf life and to increase the way people can use this technology to produce the foods. On the other hand, we are talking about, I was talking about the bioactive compounds that we can obtain from seaweeds, but there is also a problem related and how we can incorporate these bioactives to to develop fortified foods without they losing the functionality. And so this technology must be combined with other technologies like microencapsulation or electrospinning to help to include those bioactives that can come from the marine resources and to help to maintain the functionality. Otherwise, this is not a functional food or a fortified food to help restrictive diets. And there's not a lack. There's a lack of studies related to develop new printable materials, and the way we look and we study the characteristics of the specific characteristics for printing. There are the printable materials are divided in natively printable gels, foods, non-printable foods, and alternative ingredients. So when we are talking about marine resources, we are looking for a non-printable food by nature, but we have alternative ingredients like seaweeds. And those seaweeds are also rich in hydrocolloids that can be mixed with fish to help and to produce a printable food, a printable biomass to be used both for using an extraction process, but also considering selective deposition powder system that is not commonly used in the food sector, but can be promised technology to increase the nutritional value of these food products, because we can combine different powders in different locations. So we can improve the texture, but also we can improve the nutritional contents of the food. So this is a challenge, how to use fish and how to transform fish in a printable food, and how to use seaweeds as a sourse of hydrocolloids, also has a source of binder. If we look for the binder jetting technology, but also to help to the increased amount of bioactive compounds in the products. Regarding the use of those marine resources, studies are lacking, and we need to combine expertise with people with knowledge, background in marine resources properties, and work together with expertise in 3D printing to identify and optimize the formulations based on these on those unexploited fish, but also introducing seaweeds, microalgae. There are a couple of studies with microalgae, but not with seaweeds, and corresponding those formulation to the rheological properties that are needed, because they are critical to food ink extrusion, and self-supporting ability should be studied also. So additionally, seaweeds can be also considered as a fat substitute, but also a texturizer, and also a colorant, which is an important source for the extrusion process, because color is something that normally is decreasing in the extrusion process, but also has a salt replacement, looking for some healthy foods. And some final remarks from this point of view, using our knowledge in marine food resources, to combine this knowledge with people that are working with 3D food printing. Fish discards are a worldwide phenomenon, and it's a subject of great concern on the part of all the players. Seafood byproducts are very rich in high biological value nutrients. Algae or seaweeds are a good source of nutrients and also bioactive compounds, and are essential for a balanced diet, and have been demonstrating the potential to be applied in functional and fortified foods development. 3D printing opens new doors to develop innovative strategies to the valorization of unexploited fish and byproducts, but also to increase the consumption of seaweeds. And this 3D printing technology can help to promote the consumption of alternative nutrients through the incorporation of these nutrients and bioactive compounds between layers, strengthening the food products without their presence being noticed. And just let me finish with the role of, in my point of view, what are the role of the science. So we need to innovate, we need to discover, but we need to communicate and share, and to join expertise to develop, to increase the knowledge and to go one step ahead, but also to unite the people of the world and to find some ways to guarantee the food security, but also guarantee the sustainability of our world. Thank you very much for the opportunity. And if you have any question.
Thank you very much for a fascinating insight into the marine world. Before we move to questions, I could perhaps just use this opportunity to announce that in the International Manufacturing Forum series, for each session each month, we have a short poll that we would like each of you to complete at the end of today, which is where you vote for what you think was the best presentation, and then that person will receive a fantastic prize and certificate. And so I think Renato will place the link to the poll in the chat box at the end of today, so that obviously you need to listen to all of the talks before you can select which is the best. So now we can move to questions.
I just forgot to say that given the opportunity given by Antonio, I don't know if Antonio is still here, but I will be delighted to work also with the Antonio group, and I will send an email later related to our first experiment using marine resources and has a biomass for the 3D printing process. We are still in the first steps.
Hello, hey.
See, yes, yeah, I was just saying that I will be very delighted to work with your group, because we are doing our first steps in this technology, working with Professor Mitchell, with our colleagues from the technology, mechanical engineering, and our idea actually is to optimize the technology, giving our expertise and our knowledge in food science. We are trying to work together with the Professor Mitchell, and that's our plan, how to improve, to optimize the technology, that they have the knowledge to increase the possibilities to be used in the food sector, and to increase the way we can the number of the foods that we can use, the printable formulation that can be used in this field. So
yeah, absolutely. Maybe we can discuss first by email, and then the next 2 or 3 days maybe we can have a meeting online just to
I will send you today an email, because I will send you an email just because we are giving the first steps, and we are combining expertise, trying to use seaweeds, but also the marine, using marine resources, and see how can be used, combining with other.
I also use it in a paper that now is under submission, microalgae, not for 3D printing, but I use it for in application with my vacuum impregnation. So I impregnated with microalgae some ready-to-eat apple slice to improve the content in protein and also in micronutrients.
Okay.
But yeah, absolutely,
Okay.
absolutely.
Thank you very much.
Thank
Perfect.
you.
Right. So questions, Joanna, you look like you were going to ask a question.
Yeah, I have a question.
Yes.
Yeah, thank you very much, Maria, for your nice presentation. It was really nice. I have well, it's a question, it's a thought. I would like you know your opinion. So as you know, at least a half of the fish biomass is not used for food uses. So, for example, typically in a tuna can factory, the waste streams represent around the 50% of the tuna, of the whole tuna weight in the factory. So I mean heads, bones, skins. Do you think that we could use these streams, waste streams, to do something similar to the surimi? So something, I don't know, some restructuring using, I don't know, transglutaminase or something like this to create food ink for fish products in a similar way that is done in the meat industry?
Yes, yes and no. Because we need to look at the nutritional value. I believe that those side streams can be used in a different way. Actually, now the seafood industry must take care of this side stream using low temperature, so they can be used in the food chain nowadays. But the question here is how much nutrients can be extracted from that. But if we look at the meat example, the mechanical separated meat, the nutritional value is not so high than if we look at the muscle, the meat. So we need to analyze those side stream. I believe that the skin can be a valuable side stream to be used as a fooding, mixed with other things, because we can find some nutritional components that can be interesting for people. If we look at the supplements, there's a lot of food supplements that are extracted from the side streams, the seafood side streams, like the collagen, like the omega-3. So we can partially use. We cannot use all the side streams, I believe. But the point here is how to separate the side streams for the seafood industry is not very easy. So that's why I believe that we can start to look with the bycatches and the unexploited fish. And then see if the side streams can be, there must be a high value to the side stream so then the seafood industry see it has a economic value and can be able to separate or to use it in different way.
Understand. And another question is regarding big problem that is currently present in the fish industry, which is anisakis, this parasite.
Yes.
I wonder if these new technologies like 3D printing could be a solution to develop a new family of fish products without anisakis, because right now the anisakis is really spread by practically all the species, the commercial species, I mean.
I don't know, because normally we use it low temperatures, like the freezing temperatures, to prevent the anisakis. So that's the point. When you're eating sushi, we need to use frozen fish to produce sushi because of the anisakis. but I don't know. I don't have enough information. I don't really think, because we need to guarantee if they will be in a, I don't have the answer. But maybe, but
okay, thank you. No, it's just to know your opinion. Yeah.
Yes, but normally we use it low temperatures. But another opportunity for the side streams could be also the extraction of gelatin. That can also be useful to develop some to increase the viscosity of some materials.
Mm-hmm. Yeah, that's right. Thank you.
Yes. If I could make a comment, sorry, on your question, I think one of the things that's very limiting, this is true in all additive manufacturing, is the design of things. So although we talk about generating food,
yes,
we don't have the tools or the expertise in terms of the human resources to design foods from the ground up, which is, I think, inherent in your question, because there could be many ways of doing it. So
yeah.
Which is why the food, of course, is still one of the last craft industries to survive, because we can't make this more greater step to be able to generate things from the bottom up. And I think it's as in other areas of additive manufacturing, design is one of the key developments which is holding back real progress. And I think this is true. And so fortunately, so this is just a small plug for the April edition. In the April edition, we will be addressing design in digital manufacturing as a topic. And so maybe, I don't mean we will be have people talking about designing food, but this idea of designing up from the microstructure, from the nano, the micro scale, to generating macroscopic objects, I think is a huge step that additive manufacturing as a whole has to make, whether it's in making plastic products or whether it's making food products. Other questions?
I think Roberto Gamboa has one question.
Yes.
Yes, if I may, thanks for the presentation. Quite interesting to link these ocean and food realm with these more technology related 3D printing. One of the issues that you presented, and I think it's one of the key issues, is the fact that at least fish is very perishable. So my question was, what kind of routes do you see trying to use these fish in a longer term in order to be able to be a real source for these 3D printing? Should we have to make it as a powder? Should we? Well, what are your views on that? Thank you.
Thank you. Actually, in my point of view, and for the food industry, there are different 3D printing technologies, and one of the most used is the extraction technology. But the problem is that we need to have the high viscosity liquids, which is not very interesting for the food industry. So what I'm trying to study, and what I'm trying to work together with the CDRSP, is to look to the selective powder deposition technology. And so what we are trying to see is how to transform marine resources into powder using this technology, but we need to combine different powders to construct the structure. That's the point. So we need to find some binders. And so if we change marine resources that are very perishable by nature into powders, the shelf life will be increased, and so we can have it in our home, in the industry, to produce the products. So that's the point. Of course, should be how to transform the food into printable biomass, but of course, this biomass must have a high shelf life. Otherwise, it will be not interesting for the industry. But we are just thinking how to do it and how should be the way and how to get it.
Okay, thank you. Other questions, comments? Sorry, Roberto, I've just seen your chat comment. Sorry, I didn't see it earlier.
Yeah, that's okay.
Right, so if there's no further questions, thank you very much, Maria. You've broadened our horizons greatly. And now we have a break for lunch, where if you have a 3D printer in your kitchen, maybe you can have some 3D printed food. If not, enjoy your lunch. And we will restart at 2:30 with the presentation from Lorenzo Pastrana. So enjoy your lunch.
Okay, so thank you.